These notes today are a continuation of the notes we started last week on current and resistance. I'm going to speak fairly quickly today to keep this video file short in size, but please stop the video at any point just to think about concepts or to try out a problem. Tomorrow we're going to do our circuit lab, and it's going to be 3 days, so it's important that you take good notes today so you can do well on the lab tomorrow. The first thing we're going to talk about is potential difference, electric potential, and voltage. Now these words are interchangeable with each other, and it's defined as the amount of work done per unit charge. So we think about different things that have a voltage, so something like a battery or a wall outlet. In order for electrical appliances to work, they need to have that power supply or that power source. So if we think of a battery, for example, there's a positive and a negative terminal. There is a potential difference or a voltage between those two terminals. And if we plug it into a circuit or into any electrical appliances, which essentially are circuits, there is that potential difference, and that is what allows charge to move. So we look at the statement below. So electric potential is what causes current or movement of charge. Now it's important to note that electric potential does not equal potential energy. Potential is a change in energy per charge, but they don't mean the same thing. So just be careful with those words. If you don't see the word energy and just potential, that's electric potential, not potential energy. If we take a look at an analogy to water inside of a pipe, if the water level or the pipe is leveled out parallel with the ground, let's say, then the water is not going to flow because both ends of the pipe has the same potential, so to speak. But now if we tip the pipe over, now the water is going to start to flow towards the bottom of the pipe and start to leak out. So if you think about different things like maybe something like an electrical fence, this is a cool concept because we know electrical fences have a voltage, a potential difference. Now if you grab a live wire on a fence and you're standing on the ground, there's a big difference between what you're holding in your hand, let's say 10,000 volts, and standing on the ground where you're grounded, there is a large potential difference there. But if you, let's say, hold on to a wire that has a certain voltage, but your body is only touching that wire, then you would be fine. And this is why things like squirrels are able to run on electrical power lines. They don't get electrocuted because their body, their feet are on the same electric potential, so there's not a difference, so there's no current running through their bodies. Current is the ratio of electric potential to resistance, and this is known as Ohm's law, and this is the most famous equation in current electricity. V is equal to I times R, so the voltage is equal to the current times the resistance. So something that has a higher resistance is going to have less current running through it when subject to a voltage or a potential difference. V is electric potential or voltage, and it's measured in volts, fairly easily to remember. One of the most common misconceptions with current electricity, people often ask how much voltage will kill a person, but it's actually interesting. It doesn't depend on the voltage that a person is subject to. It's the amount of current that runs through them. So when the human body is dry, voltage or your resistance can go up to a magnitude of about 100,000 ohms. In some cases, maybe even larger. And every body is different. Every person is different internally, different sizes, things like that. So it does vary a little bit. But when your body is wet, the resistance of the human body can actually drop to as low as about 1,000 ohms. So comparing the two numbers, it's a big difference. So now we take a look at the chart here that's presented, and this is the effect of current or electric shock on the human body. So something like 0.001 amps can be felt by a human, by some human person. Now, something like 0.07 amps, which is significantly larger, about 70 times larger than the first one, if it goes through the heart and it lasts for more than about a second, it can actually be fatal in many cases. So this chart just allows you to see how much current is necessary to potentially kill a person. Our bodies, although we are conductive, are not meant to carry charge. We are not meant to act as conductors, so to speak. So even a little bit of current can do a lot of damage. But luckily for that, our bodies do have a large resistance, as we saw in the previous slide, somewhere in the vicinity of 100,000 ohms when dry. Please take a minute to pause the video now and try these next two questions. So for the first question here, 2000 volt fly zapper, that's the voltage, and we know Mr. Bozar's body has a resistance of, when dry, has a resistance of about 100,000 ohms. So we go and solve for the current, and that's 0.002 amps. And if we look at our chart, that would fall somewhere in this vicinity range. So it would definitely hurt, and definitely contract the muscles a little bit, loss of muscle control. And this is actually a true story. I do have a fly zapper, and I did do this to myself, and yeah, my knees got a little bit weak, so it was a fun experience to say the least. Now for the second part, it could have been a lot worse. Had my body been wet, maybe I perspired a lot, maybe I was outside running. You can see that with the resistance going down significantly to something as low as 1,000 ohms, the current was about 2 amps. Now, does that mean that would kill me right away? Not necessarily. Again, it depends on a variety of things. In this chart here, it's saying if it goes through the heart for more than a second, it can kill you. So even if I had run and I actually tried this, I probably would still be okay. But it could have definitely been worse had my resistance been lower than it was because of maybe perspiration or maybe I just took a shower or something like that. Next, we're going to briefly go over electrical power. So we've talked about power before within mechanics, something like horsepower, mechanical power. But electrical power is the rate at which electrical energy is transferred by its circuits. So we still know power is work divided by time. Work is charge times the electric potential voltage, and we saw that equation above with electric potential. And using some substitution of equations, we ultimately get an equation that is on your equation sheet, P equals IV. So power is equal to current times voltage, and power is always measured in watts. So electrical power is kind of a cool concept, and your parents pay the energy bill, the ComEd bill, every month. Now, you pay based on how much electricity you use, how much energy you use, and that is determined by the power ratings of different household objects, appliances that you use. So something like a washing machine has a much larger what's called power rating than something like I don't know, electric toothbrush or a phone charger. A good example, a phone charger that's plugged in maybe longer than or used longer than a washing machine or something like that. So different power ratings will affect the amount of energy that's used. So go ahead and pause this video for a minute and try the next example here. A hair dryer has 12.5 amps of current flowing while plugged into a standard 120 volt outlet. Go ahead and answer parts A, B, and C, and then continue the video to see if you are correct. So part A, power equals current times voltage, so 12.5 amps times 120 volt outlet. Some volt outlets are actually about 110. I believe they decreased it a little bit. But anyways, comes out to be 1,500 watts, or I'm going to call that 1.5 kilowatts, and you will see in a second why I did that. So the same number, we'll say 1.5 kilowatts. So B, if left on for 2 hours, how much energy does it consume? And this is usually measured in kilowatt hours, which is why I converted to kilowatts in part A. So power, we know by definition, is work over time, or the amount of electrical energy used over time. So again, when your parents pay the ComEd bill, they pay for the energy you use. So using this hair dryer for 2 hours, we plug in our values and we see we use 3 kilowatt hours of energy. So energy can be measured in joules, but kilowatt hours is another unit of energy. And then see if ComEd charges 8 cents per kilowatt hour. Actually, currently, right now, it's a little bit higher. It's about 12 cents per kilowatt hour. I just checked the other day, but let's just